Let us continue with our mini series of lectures on model predictive control. In the first lecture on model predictive control, I talked about the general philosophy of model predictive control and used a picture to explain the basic ideas in model predictive control. And I said there are three important ideas. One is the use of the model directly in controller computations. And the second thing I said was we introduced this notion of horizon. Instead of just saying that I want my error to go to 0 right away, I look at the error over a period of time into the future and then try and see what I can do currently to make sure that the errors in the future are minimized. So, when we talk about errors in the future, then it also gives us an opportunity to think about the control moves that I will make in the future. I am not restricted to just thinking about the control move at the current time. So, there is a horizon in which I am going to decide what control moves to make and a horizon in which I am going to decide how the errors should behave. So, that is the basic idea of a model predictive control, and the horizon in which I am thinking about how the errors should behave is called the prediction horizon, and the horizon in which I am thinking about what control moves to make is called the control horizon. Now, the final aspect of model predictive control is actually putting all of this together as an optimization formulation, so that the model predictive controller problem can be solved. And when we put all of this in an optimization formulation, then the solution to the optimization formulation gives me the control inputs. So, the control inputs are not written as analytical expressions, but they are a solution to an optimization problem. So, we were working with this picture in the last class. This is a notion of the control horizon. So, this is where I am going to make these moves, and I am going to look at a prediction horizon which is generally larger than the control horizon, so that I can kind of think about and change the behavior of the error in a prediction horizon. And the key aspects of this figure, the other key aspects of this figure are that this is the past, things that have already happened, and this is into the future. And we also said that we are moving away from the continuous framework and we are looking at all of this in a discrete framework. So, we have to keep that in mind. Now, when we talked about optimization problems in the last class, I said there are three major components in an optimization formulation. Number one is the objective function. Number two, the constraints in the formulation. Number three, what are the decision variables. So, if we understand each of this carefully, then we understand the optimization formulation. Okay. Now, the solution to this optimization problem, in case where there were no constraints, I showed you in the last class, and if it is a univariate optimization problem, we saw that for a function to take a minimum value, the first derivative should be 0 and the second derivative should be positive. And in a multivariate problem, for a function to take a minimum value, the first partial derivative with respect to all the variables should be 0, and the second partial derivative, which is written in terms of a matrix called the Hessian matrix, should be positive definite if the function takes a minimum at those values. Okay. So, that is a solution to the optimization problem in an unconstrained case. In a constrained case, it becomes a lot more complicated, and a typical optimization course will talk about that. However, as far as this course is concerned, what we are going to do is we are going to simply formulate the problem and then use optimization solvers that are available with all software programs that come now, such as MATLAB, Scilab, and anything else that you might think of. So, basically we are going to use the optimization program to actually solve these problems. We are not going to do this analytically, except to kind of understand how this works, and which is what I showed you in the last lecture. So, if we were to now formulate the MPC control problem, essentially we have to take these notions of prediction horizon, control horizon, and then basically say how does this translate to the three components in an optimization formulation. The first component being the objective, the second component being the constraints, and the third component being the decision variables. Now, let us start with an objective. So, what I am going to do is I am going to literally say in words what we want in terms of an objective, and then I will show you how that translates into an objective function mathematically. So, if I were at this point right here, I said I already have a measurement at y of k. So, basically what I can do in terms of manipulating or modifying or shaping the error in the future has to start only with time k plus 1, and remember time k plus 1, when I write k plus 1, I have already said the true time is k plus 1 times Ts. We are only doing it at discrete time intervals. So, what I can do is I can think about modifying the error, and since I have taken a particular prediction horizon, I can think about modifying all the errors in this prediction horizon. So, if you think about p time steps into the future, then y k plus 1 given k, which is a measurement which I do not have yet. So, that is something you have to remember, because we are doing all of this sitting at time t equal to k. So, I am predicting into the future what the measurements will be. So, basically I need to somehow figure out how I am going to do that, but for now let us assume that I have somehow predicted what the measurements will be in the future. Then I can basically say the error at each time is the difference. So, if I take this difference, that is the error between y k plus 1 and y set point. At k plus 2, this is the error, k plus 3, this is the error, and so on. So, I will get these errors. So, you might call in some sense error at 1, which is k plus 1, error at 2, and error at the pth future time instant. So, let us say I have these errors, and from a control viewpoint, my interest is in minimizing this error. So, somehow I have to collectively minimize all of these errors E1 to EP. So, when I try to minimize, the first thing you can think of in terms of objective function is to say, let me minimize E1 plus E2 all the way up to EP. Okay. So, this basically I can write as I equal to 1 to P EI. Right. So, this is something that I can do, but you will notice right away that there is a problem with this. The problem is, for example, if I have something like this. So, I have this point, and then let us say I go here and then come down here, then I could have positive and negative e's, which will make this become smaller and smaller. It can even take it to 0. However, the problem will be that each of the errors themselves will not be 0. So, if you are minimizing, the other thing is the idea is to take the errors above set point, in which case all the errors will be negative. So, from a minimization viewpoint, it is a good thing to keep getting smaller and smaller values. So, in which case the E1s can become very negative, and you will still be minimizing this, but your objective is not that. Your objective is to ensure that E1 to P are all as close to 0 as possible. So, just adding them up will create all kinds of problems, and you cannot really use this as a minimization objective. So, the minimization objective that people usually use is to say, let me minimize not sigma EI, but EI squared. So, what this means is, instead of minimizing E1 plus E2 plus E3 and so on to EP, I want to minimize E1 squared plus E2 squared plus E3 squared all the way up to EP squared. Okay. Now, what happens is, whenever we try to minimize, that means the lowest value this can ever take is already known, which is 0, because this is sum of square, and that 0 you will get only if each of these terms are 0. So, since no term has the ability to become negative, all of them are positive, the lowest value is 0, and the lowest value is achieved whenever E1, E2, E3 all the way up to EP are 0. So, if even if you have one negative, that squared will be a large positive value. Okay. So, basically the idea is, instead of minimizing sigma EI, you minimize sigma EI squared, and if you minimize sigma EI squared, then you are guaranteed, when the optimization objective keeps going down, collectively all the E1 to EPs are going down. It is not possible for one to become very negative and so on. Okay. So, that is the key idea. So, if I want to collectively minimize all of these errors E1 to EP, basically I do a sum of squares, and minimize this so that the least value I get. So, this is called the least squares problem formulation. So, in this case, since we are already at k, the first error ei is actually the error between the k plus 1th instant in the future and y set point. So, if you look at this, what if I expand this, what this will give me is y of k plus 1 minus y set point squared, which will be the error 1, the first error term, plus y of k plus 2 minus y set point whole squared, and so on, and the last term will be y of k plus p minus y set point whole squared. So, these will be the p terms in the objective function. Now, if this objective function is minimized, then each of these errors are minimized. That means, whatever I have predicted in the future in terms of what the measurement or the output value will be, those are actually pretty close to the set point, because each one of these terms is going to go smaller and smaller. When these terms go smaller and smaller, that means the difference goes smaller and smaller, that means the output is very close to the set point. So, from a control viewpoint, the objective of minimizing the errors collectively is taken care of if I look at an objective function like that. So, that is the first component of the optimization problem, which is basically the objective function. Now, when we look at this, we say okay, this objective function is something that we have defined already. Now, how do we define the other two components of the optimization formulation? So, once the objective function is defined, the top portion of this picture we are kind of done with. Now, we are going to focus on the bottom part of the picture, and the constraints are generally going to be on the inputs. There could be constraints on the output also. Those are more advanced formulations which we are not discussing here. So, let us look at the bottom portion of this, and this is where the manipulated variables are being shown. So, the idea is from a model predictive control viewpoint, what we said was we want to make these control moves in such a way that the errors are minimized. So, we have anyway posed the minimization of errors as an objective function. So, that is taken care of. Now, what is this move plan is something that we have to see. So, the moves that I am going to make. So, remember we are still talking about a single input single output control. So, there is only one u, but since there are many control moves that I am going to make, that is I am going to make this formulation identify the values that I should keep for these input variable at different times. I am going to think of each of them really as a variable. So, I might say the variables that I have, and which I will come back to in the next slide, are uk plus 1 all the way up to uk plus m minus 1. So, conceptually what we are saying is I have already got a measurement. After I got a measurement, I have checked whether the measurement is close to set point or not, and so on. So, that is a different computation. After that, from a control viewpoint, what I need to do is I need to make the first control move at time t equal to k, and clearly because always control moves take some time to affect the output, this is already there. So, it is not going to get affected. So, from an output viewpoint, every output after this move is made is going to be affected, but since we are looking at discrete formulation, we are looking at outputs at specific times k plus 1, k plus 2, k plus 3 and so on. So, because of this input move, y at k plus 1, k plus 2, k plus 3 and so on will be affected, and what we are saying is unlike the standard PID controller where we will look at this move in a continuous domain though, what we are going to do is, since we are anyway talking about a horizon over which we are looking at minimizing the errors in the output, we will also look at a horizon in which we are going to plan our manipulated variable moves. So, this is uk value which is as yet unknown. So, we do not know what this value is. Only when we know this value will we be able to predict. That is how we are going to connect these values to the predictions through a model, which we will see later. As of now, if you just think about these as variables, so uk is a variable for which I need to find a value, uk plus 1 is a variable for which I need to find a value, uk plus 2 is a variable for which I need to find a value, uk plus 3 is a variable for which I need to find a value, uk plus 4 is a variable for which I need to find a value, uk plus 5 is a variable for which I need to find a value, uk plus 6 is a variable for which I need to find a value, uk plus 7 is a variable for which I need to find a value, uk plus 8 is a variable for which I need to find a value, uk plus 9 is a variable for which I need to find a value, uk plus 10 is a variable for which I need to find a value, uk plus 11 is a variable for which I need to find a value, uk plus 12 is a variable for which I need to find a value, uk plus 13 is a variable for which I need to find a value, uk plus 14 is a variable for which I need to find a value, uk plus 15 is a variable for which I need to find a value, uk plus 16 is a variable for which I need to find a value, uk plus 17 is a variable for which I need to find a value, uk plus u k plus 2 is a variable for which I need to find a value, and so on all the way up to u of k plus m minus 1. So, if you take a look at this, there are these m variables for which we need to find a value, and based on these values the output will change. So, the idea of optimization is how do you choose these values so that these outputs are as close to y set point as possible. Okay. So, that basically means if I make some decisions for this, how will it affect the output is something I should bring in. That is where the notion of model comes in, which we will see as we go along. But as far as we are concerned, these are the variables, and the constraints are written in terms of the decision variables or functions of decision variables, as I talked to you before. So, you might say if I have a control input such as a flow through a pipe, we already discussed this, there might be a minimum value and a maximum value that it will have. Minimum value if its flow is going to be 0, or the maximum value is going to be when I keep the pipe completely open, what is the flow, and so on. Okay. So, every value I take here, u has to be between u lower and u upper. I have generically written this for the input u. So, since each of these variable represent the same u at different times, so this constraint should be obeyed by every one of these. Okay. Though I have uk plus 1, these are the same inputs, but at different times. If the general input itself is constrained between lower and upper, then the input at every time instant should also be constrained between a lower and upper. So, basically if I want to generalize this and write this, so this is on the u input itself. If I want to generalize this and write this as constraints at every instant in which I make a change to the u, so I will write this as u lower less than equal u of k less than equal to u upper, and this is a mathematical notation for all k. So, irrespective of what the k is, because this u of k is still representing the same input, but at different times. Okay. So, that is the constraint you have. So, this is written generally, but you have to write this for u at every time instant. So, those are constraints on u. And similarly, when we make a change, so this basically talks to some constraint generally on the u itself, right, what values it can take, where it should be. So, that is one type of constraint. The other type of constraint is at a particular time, how much can I move this u by. So, if I am here, okay, so if I move this here, so the difference is this point was u k minus 1, this point is u of k. So, if I define a delta u at k as u k minus u k minus 1, so this is where I was at, and once I get a u k I come here. So, the delta difference is this u k minus 1. Then what typically happens in control systems is there will be a constraint in terms of how fast I can move my control valve, right. So, in a very short time in which I am going to take my manipulated variable to a new value, what is the rate at which I can do this. So, I can directly give a constraint on delta u. Now, again I have written this as for the input itself. So, this delta u change basically tells you how much you can change at a particular sampling time, and much like how I wrote here, here also I have to have delta u lower less than equal to delta u k, and delta u k is always defined as the difference between what value I choose at k and what value it was at k minus 1. So, if it is u k plus 1, it will be the difference between if it is delta u k plus 1, it will be the difference between u k plus 1 and u k, and so on. So, much like how I said this is for the actual control input, and this has to be applied at all u k's, this delta u is also for the same control input, but at different times I am taking these deltas. So, this is also applicable for all k's at a different time instance of making the control move, then I will have this delta u upper for all k, very similar to what I had here. So, these are the types of constraints that we look at when we formulate a model predictive control problem. Now, this constraint spoke about this. Now, this constraint says whenever I make a move, what is the limits that I can kind of achieve, right. So, some limit that I have. So, while there is an overall limit in terms of the actual value itself, there is also a limit. There are this limit to be applied on delta u every time I make a delta u. So, in other words, if I am here, I cannot make a delta u like this, is what it says. There is a limit on this. So, in this case, clearly the way we have drawn this, the delta u will at least be something like this, because all of these values should be within that limit. Okay. So, this delta u limit will be fixed in general, or you could make it change over a period of time. So, if this is the fixed limit, then you can say this is the maximum delta u you can take, or you could have things where this changes from sampling time to sampling time if your application really calls for it, but in general this is actually a physical hardware constraint. So, you will say this is a maximum delta u I can take. Now, we have talked about two of the components of the optimization formulation. One is the objective function, and the other one are the constraints, and the constraints are of two types. One is on the range of u itself, and the other one is on the range of delta u. So, once you have these two, the third component is actually the decision variables, and the decision variables are the variables for which I have to find values, and in this case I have to make a decision about the control move plan. What are the control variable values that I am going to have. So, this is the same control input, but at different times, again just to reiterate. So, I have to make decisions about what value this control input will take at time k, at k plus 1 all the way up to k plus m minus 1. These are the m variables that I talked about. Okay. So, now you see how the MPC formulation has become an objective, an optimization formulation. From this picture, if you understand these equations, then you have basically understood the main concept of MPC. So, the objective function tells you that you are trying to minimize the error. In some cases, when you want to generalize this, you might say I do not want to just minimize the error, but I also want to minimize the control effort that I take, which is I do not want to take very large control moves u, because that takes money and effort. It might be that the objective function is not only the error square that I have, this is the generalization of the formulation, but also this u squared. What this u squared tells me is, if I take very large control moves, this will be large, which will be bad for minimizing the objective function. So, I want to keep the move sizes as small as possible. So, in some sense what it says is how close can I get to my set point without expending too much effort, which is typically what we do in all of the problems that we solve. So, we have a goal, we want to get to that goal. At the same time, many times we want to see what is the kind of minimum effort that is possible to get to this goal. Not simply because maybe we are lazy, it is because once you minimize the effort towards this goal, you have more time to pursue other goals that you have, that you want to pursue. Very similar idea in control. So, this is your pursuit of your goal, which is going to the set point, and this is the effort that you need to put into getting to that set point. So, in some sense you want to minimize both of this, that is, you want to minimize how far away from the goal you are, and you also want to minimize the kind of effort that you are going to put in. So, this is the objective function. Now, the beauty of model predictive control formulation is that you could just do this part of the objective function, or you could add both of this, or you could weight these objective functions using weighting factors, which will tell you what is the relative importance of this. If lambda 1 is much greater than lambda 2, then the importance is I want to be very close to my goal, irrespective of the amount of effort that it might require. But now, if you say lambda 1 and lambda 2 are kind of scaling them, so that these terms are equal to each other in magnitude, then the question is, well, I want to get to my goal, but I want to have a balanced life. So, I do not want to do crazy effort, I want to also kind of balance between how fast I achieve my goal and the amount of effort that I need to put in. So, once you have these things, then you can start thinking about these objective functions more conceptually, and then you can formulate objective functions that you can solve. Ultimately, if you are simply going to solve this as an optimization problem, you could even come up with any kind of nonlinear objective and then say let us solve this optimization problem. So, what you are doing in model predictive control is you are moving all the effort into solving this problems to an optimizer, and as long as optimizers keep getting better and better. So, you have better nonlinear optimizers, you have better constrained optimizer and so on, then you could actually formulate any problem you want, and the formulation is very intuitive. You know why you are writing each objective function term, and the formulation becomes intuitive, and the solution you do not ever worry about, because it is an algorithm that is out there which will solve an optimization solution. So, that is a key idea here. So, this is objective. We already talked about these constraints. This I have generically written for u. So, this should be converted to uk at every k, because the uk also represents the same u. Similarly, delta uk also represents the same input. So, this should be applied at every time instant, as this would be applied at every time instant. So, this is the constraint part of the objective. From a control viewpoint, what this physically says is that the input moves that you are planning should all obey physical constraints such that this objective is minimized, and I have these as the decision variables uk plus 1 and so on. So, just to be sure that we make this explicit, so when I expand this, I will have u lower less than equal to uk less than equal to u upper for all k. So, I can even say, so since I am using k here, so let me use I here, ui for all I k plus 1 to k plus p. Okay. So, this is how this is expanded. Similarly, you can also expand this, and this k in this slide talks about the time instant at which we are sitting, and then this is all prediction into the future, and these are control moves into the future uk plus 1, uk plus m minus 1 and so on. Okay. Sorry, this is going to be k to k plus m minus 1, because this is talking about the control move. So, this is how combine this and put together formulation for model predictive control. Now, in the last slide we talked about the formulation, we talked about the notion of horizon and how all of these are combined into a mathematical formulation. So, the next question that you might ask is, okay, where is the model in all of this? So, you have written y, you have written u, you have written an objective function, and you have written constraints and so on, but where is the model in this? So, as I said before, remember when we talk about this, when I am sitting at time t equal to k, I have this output and I have these inputs I am going to make. Now, I do not know the values of this, and I have not made decisions yet about these also. Okay. However, the formulation is going to relate the decisions I make to what happens here, right. So, if I want to make decisions here, then I should somehow figure out what is the effect of these decisions on the output, so that I can actually say this will be the effect, and I want to compare that effect whatever I get with a set point. Okay. So, that is a basic idea of optimization. So, in that sense what I need really is somehow I have to connect what moves I plan to make in the future to what will be the impact, and this is where the model comes. Okay. Now, in many cases we have looked at models which are continuous models, but in this case what we are interested in is the move plan that I am thinking about are uk plus 1 all the way up to uk plus m minus 1. I want to know how these are going to affect y k plus 1 all the way up to y k plus b. So, these are future outputs that I am expecting. So, the move plan that I have when I actually implement this move plan, what will be the output, right. Now, this output I am going to check how close they are to set point, and I am going to make changes to this so that these outputs are as close to set point as possible, and this is where a model comes into picture. So, we will explain how model comes into this to complete the whole MPC formulation in the next lecture. Thank you.